All right, welcome. In this video, I want to continue discussing recursive analysis and recursive algorithms, specifically recursive sorting algorithms. And so we're going to take a look at a recursive implementation of the merge sort algorithm. So here I have a simple recursive implementation of merge sort. I think we're already fairly familiar with the sort problem, where we're going to take any list of any in any particular order, and then try and return the same elements of that list in ascending order as we've got here in our problem statement. So we've got that list coming in, and the first step in our recursive algorithm is to tackle the terminating case, of course, the non-recursive case. And in this case, the non-recursive case is going to handle the inputs when our input list is already known to be sorted. And what I mean by that is known only by its size. So we know, for instance, if we are handed an empty list, that it is in order by default, vacuously true. Likewise, if we are handed a list of size 1, then we know that that one element is in its proper location. It's the only location it could be in. And so we have no work to do in those cases, so we'll call this the terminating case, where we will just return the list back that we were handed as input. Otherwise, we might enter into a list or we might be handed a list that's larger than 1, in which case we'll enter into the recursive work that we have listed here. And that recursive work is going to start out by doing 2 recursive calls. This is how the merge sort algorithm works. It's going to do 2 recursive calls on 2 halves of the original list. Now, how you carry out those halving is sort of up to you. That is actually not important to the merge sort algorithm. You could take, as we've done here, the first half from A1 up to the floor of n over 2, of course the floor showing up again in case n happens to be odd. And then the second half, starting where we left off at the next element, the floor of n over 2 plus 1, and then going up to a sub n. That's one way we could split it. However, we could have also put the evens and the odds, or it's not any other split that we would like into 2 equal halves. Now, the goal is to try and get those 2 halves to be as equal as possible, but it is also not important to the algorithm that they are equal. We could just take 2 random chunks, sort one and sort the other. We just happen to get the best performance when they are as close as possible, as these 2 are. These 2 will be equal in size in the case of a even n, and they will be unequal in size, but only differing in size by 1 element if n happens to be odd, which is something you can test yourself with these values and the floor function by just trying out various values. Now, simple values are maybe 1 and n, where you pick an even n or an odd n, or other values are where you vary also the starting index 1, as we can see here, that in this subset we're going to get an arbitrary set of indices starting at somewhere in the middle instead of starting at 1. So even with different indices, we can still probably find that this is going to result in a middling element, or the middle element if such an element exists. All right, what do we do after we've sorted the left-hand side and the right-hand side, as I've got here? I've stored them in these temp lists B and C. Well, we now need to merge those 2 lists together back into one single list. And to do that, we're going to call the merge subroutine. Now, I've got a little note here. Those of you who are familiar with the merge sort algorithm may have looked at this in more detail before, but the merge subroutine is a subroutine that, as it says here, merges 2 sorted lists into one sorted list. So we haven't really said how we do that here, so you might have to go take a look and see how that is done. But the important thing for us is that it's going to use a number of operations in theta of n plus m, where n is the size of A and m is the size of B. I've got this this notation a little off from what my pseudocode here is. This should be B and C, but the goal here is, of course, of the 2 lists that we pass in here, do we have one might be of size n, the other might be of size m. If we're lucky, we're promised maybe that they are the same size as we were hoping to get up here in our split. If we did, then this might just be theta of n. But we've put n plus m in here just to be sensitive to the possibility that we might be getting different size lists. Now, of course, even when we get a different size list here, the difference will be n over 2 or n over 2 plus 1, roughly, maybe the floor showing up in there, of course. But if we have that difference of just 1, that's not going to make a difference in the theta at the end as well. But we'll keep that in mind as we continue our analysis. Okay, so now we want to do our analysis for this pseudocode that we've created, maybe not knowing exactly how many operations this is carried out, only knowing that it is theta of n plus m. So now that we've got the algorithm, let's see if we can build a recurrence relation. Well, I have a recurrence relation right here, but let's see if we can sort of verify this recurrence relation ourselves. The 3 is the same 3 that we've had in our previous examples, accounting the one call, the comparison, and the return. Now, that's going to, as I mentioned in earlier videos, that's going to be a fairly standard as long as we're writing our pseudocode and counting our operations in this way. But as we're going to see in this particular analysis, but also as we get into future analyses, that at some point we are going to step away from counting exactly what this constant is and instead just giving it a name. And in my video series on the design and analysis of algorithms, I typically just call this constant c instead of counting explicitly what it is. And that's because sometimes we don't know what it is. It depends on an implementation that we don't actually have access to. So here I'm going to leave it as a 3, but we can imagine changing it to a c down the road. Now, let's look at the rest of the recurrence relation we've got here, because it's a lot messier than the recurrence relation that we've looked at in the past. Now, first of all, what I've done is I've been careful to note that these two lists here, the sublists that I've created of different size, when I sort them recursively here, these t terms are telling me how much time it takes to do that recursive sorting. Okay, so that recursive sorting is carried out by this recursive call, and the amount of time is expressed by this. Now, where did I get the floor of n over 2 and the ceiling of n over 2? Well, it should be pretty clear that b is of size the floor of n over 2. So that call is the floor of n over 2. Now, how big is the other one? And this is just a little bit of math we can work with our floors and our ceilings. But if we take n, that's how many were in A, and we subtract off the ones that were in B, the floor of n over 2, what we're given is the ceiling of n over 2. And again, you can test this with some numbers if you don't believe me, but this is indeed the case. And that's because one of the elements, in the case where n is odd, one of these two lists is going to be one larger than the other, and the difference between the floor and the ceiling here is exactly 1, and that's the difference we're going to get. Now, we have the same thing happening over here. What's this term here? This is the term that's going to express the amount of operations carried out by my merge subroutine. Now, we were told by the merge subroutine that it takes theta of n plus m. Now, we might be tempted to write theta of the floor of n over 2 plus the ceiling of n over 2. Notice the floor of n over 2 and the ceiling of n over 2 are subbing in for our n and m here, because those are the size of the two lists, B and C, that we're calling merge on. Now, as I already mentioned, as we're going to see here in a second, that the floor of n over 2 plus the ceiling of n over 2 is just equal to n. So we'll simplify that one in a second. But where did this d come from? Well, the d comes from the fact that we can't write theta down here. Theta doesn't make sense down here because the theta function, remember, what it does is it takes a function like this one, n plus m, and it turns it into a class or a set of functions, of infinite functions. And we can add functions to each other, but we can't add a class of functions to a function. That doesn't really make sense. And so what we usually do when we want to write theta down in one of our expressions down here, but we don't know what the constants are, is we pick out a constant and we give it a name. We know there is some constant that, say for instance, the function that's in theta of n plus m would be less than or equal to or greater than or equal to. These constants are guaranteed to us by the definition of big O and big omega, or the definition of big theta, the one that we're applying here. And so since those constants are guaranteed, but we don't know what they are, we don't know if it's 17 or 28 or something like that, we'll just give it a name. So here, the 3, we did know what it was, we counted it, it was 3, so we didn't have to give it the name c, but we could have. Well, here, we didn't go into merge and count it. All we know is that someone else who did that effort told us it was theta of n plus m, and so we have to trust their work and pick out a constant. We'll call it d. Again, we don't know if d is 17 or if d is 12 or whatever it might be. We just know it's some constant that is guaranteed because of this theta proof. So this extra work here is expressing the work carried out by the merge. Now what about the 8? Well, I'm not actually going to iterate through because I'm trying to get to a point where I'm saying the difference between an 8 and a 9 here is not going to matter. And in fact, in a second, I'm going to lump that 8 in with this d, in fact, with this d, as we'll see in a second, just to make things simple. In fact, let's do this right now. Let's simplify this by doing a couple things. The one key thing is something we did in a previous video as well, which is assuming that n is a power of 2. And assuming that n is a power of 2 means we don't have to worry about the division as much, and we can get rid of the floor and the ceiling. But really, I'm just going to use it here to get rid of the floor and the ceiling. And so that's really only assuming that n is even, meaning it's only divisible by 2 on this level, and we'll just ignore and maybe forget about what might happen on the next level down if it becomes odd. And so here, technically we're assuming our n is a power of 2, but I'm just rewriting it here without the floor. What that allows us to do is if we get rid of the floor and the ceiling here, or rather, when n is a power of 2, these are the same term. And so I'll just get rid of the floor and the ceiling, merge them together, and now we have 2 such recursive calls of this size. And again, sometimes what I say when I'm doing this type of analysis, I say, well, I'm just going to blur my eyes a little bit, be a little sloppy in my math, drop some floors and ceilings out. Why am I going to do that? Well, one, I'm allowed to. The theta rules that I'm using are kind of a blurring of our eyes where certain things drop out and don't really matter, floors being one of them. And then secondly, my goal is, if my goal is to do this type of analysis, then I kind of want to do it a little bit easier, make it a little bit easier on myself. So blurring my eyes makes the math a little bit easier. So here, blurring the eyes allowed me to get rid of the floor and the ceiling and lump them together, and now I have a simpler term to work with. It also, well, here I didn't have to blur my eyes. This is exactly equal to an n. But then what happened to my 8? What did I do with my 8 here? Well, imagine I did a little scratch on the side and I got down to this point and I said plus dn plus 8. The fact that the dn and the 8 are different in terms of their degree, for instance, n to the power 0 or n to the power 1, that's a little bit troublesome. I know if I go work on my proof, which is what we're going to jump into in a second here, the 8's going to cause me a little extra problem. But I also know that I can probably lump that 8 in with this d. Imagine what I did, and we've done this technique in the past, is imagine this 8 wasn't an 8, it was an 8n. If it was an 8n, then we could just add them together. We would get d plus 8n. Okay, and I could leave it like that, in fact. But then why did I get rid of the plus 8 then? Well, here's the final technique. Remember what d was? D was some constant. We don't know what it was. We don't know if it was 17 or 25. We'll say it was 17. Well, now I'm going to add 8 to it. Now it's 25. Well, I still didn't know what it was in the first place. I didn't know it was 17. So now I don't know it's 25. All I know is it's still a constant. And a constant plus a constant is still a constant. Now I've been maybe a little bit sloppy here because I've used the same d above as I've used below. I might want to call this d prime. It's a new d. It's not exactly the same as before. It's maybe d plus 8 or something like that. But for my purposes, and again, all that I'm concerned with is that it's a constant, and so I'll just call it d. And I'm going to leave it as d. And basically, I maybe think of that as saying, well, I know I called this one d, well, let's call this one d now instead. Okay, just to make things easier. Okay, now, all of that simplification is so that I can work with this recurrence relation instead of this one. This one's just messier, and it means you probably could work with this one. In fact, if you really painstakingly want to go through the nitty-gritty details, you can definitely prove upper and lower bounds for this recurrence relation as well. And if you want, maybe go write the merge subroutine and find out what d actually is. d, and it's probably not just d times this, it might be d times this minus some number or plus some other number over here. Go do your own analysis and see exactly what that d is, and you could get that really, really fine-tuned analysis. Now, my experience doing computer science for a long time, and as a computer scientist, is I know that all those details don't really matter. And they are painstaking in the sense that you can fill up a few pages worth of algebra dealing with all your floors, ceilings, plus ones, minus ones, and so on. Now, I have realized that all that extra work, while it is useful in a learning environment to sort of make sure you practice those skills, once you're pretty confident with those skills, there's very diminishing returns on practicing them after that. So I've gotten to the habit of trying to instead practice my skills of simplifying it, making my math easier, finding the quicker route, finding the easiest route to my solution. So let's find a easier route or a quicker route to our solution by continuing this proof here, or rather continuing with this recurrence relation and starting our first proof. So the first proof that I want to work with here is going to be the upper bound. Now, where did I get the guess of n log n? Well, let's say for at least this video, I cheated. I went and I looked and I said, hey, what is the runtime of merge sort? And someone else told me it's n log n, and I said, okay, I believe you, I'm going to try and prove it. And that's a fair and okay way to get the answer sometimes, okay? Luckily, if you're trying to do a proof like this, the first step is guessing what you're trying to prove, and there's no rules about guessing. You can get your guess however you want. You can get your guess by applying some mathematical formula, which is something I'll present in the Design and Analysis of Algorithms video series, or you can just guess. So maybe I just guessed here. I think it's n log n. Why? Because I heard it somewhere. So that's what I'm doing. Now, the other thing that you're going to notice here is I was a little bit different. Instead of saying it's less than or equal to b times n log n, I put this plus a on there. Now, where did that come from and why? First, can I even do that? Well, let's just verify that if b plus n log n plus a, we want to show that that maybe is theta, or let's say big O for the moment, of n log n. Is that true? Yeah, the plus a we know doesn't matter, right? We could, using that promotion technique I was just talking about, we could say, imagine it wasn't a, it was a n log n, lump them together, b plus a, there we go, simple proof, okay? So the idea is that this function here is indeed theta of n log n, and when we're trying to prove that something, it is theta of n log n, but in this case big O is maybe the more important one, when we're trying to prove that something is in big O, we can show that it is less than or equal to any function that is in the requisite set that we're looking for. And so here we've just used some freedom to pick out a different function from the set of theta n log n or big O n log n. And this one we picked out with a plus a. Now why? Why did I do that? Well, imagine going with me for a moment down our proof and tackling our base case. We did this in an earlier example, but I want to teach you a different tool, a different trick for dealing with this problem. If we plug in the value we want, let's say 1, into our b n log n here, we get log of 1 is 0. All of this multiplication is crushed by that 0, so we just get a 0. So we needed to show that 3 was less than or equal to 0. We ran into this problem before. 3 is not less than or equal to 0, so it's impossible for us to prove this. Okay, well then, what does the a do to help us here? Well, let's see. Now, what I'm going to do is I'm going to plug in my n equals 1. I'm going to still get my t of 1 is 3, but now I have to show it's less than or equal to b 1 log 1, well that's still 0, so that all gets canceled out, plus this a, which is a. So all I need to do is pick a to be greater than or equal to 3. And guess what? I get to pick what a is. I didn't say what a is above. It could be any constant. Sort of implied it's positive here by the plus, okay? But here this is saying, yeah, it has to be positive and it has to be greater than or equal to 3. Okay, so what did that do for us? Well, in our previous version, when we encountered this problem, we said n equals 1 doesn't work, so we needed to go to the next base case, n equals 2 and n equals 3, which is a perfectly acceptable way to complete this proof. You're able to do that. But by doing it this way, I'm extending my proof so that my n naught, in that other example, we started our proof off at n equals 2, not n equals 1. So we had only proven it for 2, 3, 4, and up. In this case, I found a trick that allows me to add 1 into that list as well too. So now this proof will apply for 1, 2, 3, and up. Okay, so let's jump into the inductive hypothesis. So our inductive hypothesis, we're going to assume what we're trying to prove, but we're going to write it down in terms of k. So I'm going to, again, copy it down in terms of k. Notice the a comes down here too, so we need to be careful. The a is going along for the ride for the entire proof. We need to make sure it's included in all the components of our proof. Okay, so again, copying it down in terms of k, where we've just substituted out the n with a k, and again reminding it's only for the k's less than n, because those are the ones that we'll assume we've already proven it for in our inductive case. In this case, maybe it's only 1, and then we'll try and prove it is also true for n, and that's what we're going to do in the inductive case or in the inductive step when our n is greater than 1, and copying down the definition of what t of n is exactly is in that case. All right, the next step is the critical step, and it's the step that sometimes I find some of my students get a little tripped up on, and that is that we need to now do double substitution. First of all, we want to apply the inductive hypothesis to get rid of this t term. So we look inside the t term at its argument, and we see what is it? It's n over 2. Now then we go up here and we check. Is n over 2 a k that is less than n? So if k was equal to n over 2, is that less than n? Yeah, that makes sense. It looks like it is. As long as n is positive, that's the realm we live in. So what do we do then? Well, then we say if k is less than n, then that means that this hypothesis will work. So now we need to plug in the n over 2 for this hypothesis. Sometimes I tell students, go write this out again on the side. T of n over 2 is less than or equal to b times n over 2 log of n over 2 plus a. Okay, once you have that, you realize, hey, this t term here, I can replace out with this larger, messier term. So that's what we're going to do in our next step, is replace out the t term, keeping in mind there are 2 of them. So when we get to the next level, the 2 is still out front, and then let's make sure we've done this properly. So we've taken the n over 2 and we've plugged it into this business here. So we've still got the b, we've got n over 2 for our k, log of n over 2 again for this k, plus, and not forgetting, the a here. Okay, so let's continue to the next step, where we're going to just basically distribute our 2 through. The 2 is going to cancel with this one to just give us a bn log, but I'm going to leave the n over 2 inside alone for the moment. Being careful, the 2 also distributes to the a, so we now have 2 a's here. And if you're sort of putting down at the bottom our finishing line, where are we trying to get? Well, the finishing line is exactly what we have written here, b n log n plus a. So we still need one of those a's, so it's good that we have one a, but sometimes we'll split them out, and we'll see, I'll do that in a second, to split out the a I want from the other a, the one I don't want. So now what did I do in this next step is I applied the log identity to this difference. Sorry, to this, this fraction. Applying it to the fraction gives us a difference, which is we take log of the top, so log of n, minus log of the bottom, log of 2. And of course the bn is out front, so it's still there. Okay, log of the top minus log of the bottom. Plus my other 2 elements, I just slightly rearranged them over here. Now the important thing here is we know what log base 2 of 2 is, that's just 1. So simplifying it ever so slightly, and I'm going to pull one of my a's out, we're going to get b and log n plus a. All right, that's the part that I actually want. Those are the 2 terms. This was one of the terms I wanted. The other one was in here, so I'm going to pull them out. That matches my theorem, what I'm trying to prove. And then the other stuff, the extra business. Now remember, normally we say, okay, do my leap of faith here, assume that this is less than or equal to, and then try and figure out when that's true. So we could take that extra bit and say as long as that was less than or equal to 0, meaning the minus part canceled out with the positive part, we're good. Now, I'm going to move the bn over to the other side. That gives me here the bn must be greater than or equal to the dn plus a. Now here I'm going to use another little technique. I kind of want to divide by n on all sides, but dividing by n here gives me another copy of n under my a, and I don't want n's. The whole point of dividing by n is to get rid of the n's. So the thing I will do first is I will promote this. I will imagine, hey, if bn was greater than dn plus an, so making this bigger, then that means it must also be bigger than dn plus a without making this bigger. So I'm just going to pretend there's an n there. So when I divide out, it cancels, and that's going to give me this equation here. B must be bigger than d plus a. Instead of d plus a over n, which doesn't help us very much. Okay, if you got to the point where you were like at d plus a over n, usually the next thing I might do here is I would say, well, what is n? Keeps growing and growing and growing. Well, that term a to the n keeps getting smaller and smaller and smaller as n grows. So then I might say, well, what's the smallest that n is? And depending on how blurry my eyes are, that'll either be 1 or in this case 2. In this case I picked 1. I basically picked 1 with my trick that I did above, and that gave me a divided by 1, which is just a again, which you could have also ended up with a over 2 here, which is also perfectly fine, or a over actually any constant would be fine as long as we're talking about n as n goes to infinity. But for simplicity, of course, this is the easiest way to write it. So I'm just going to say b must be bigger than a plus d. So now let's go to the process of picking our constants. Conditions on a. We have two conditions on a. A must be greater than or equal to 3, and then this complicated one. B and a are related to each other in some way. Since b is only conditioned by this one, I'm going to solve for a first by picking a to be 3. And then plugging in 3 here says b has to be greater than or equal to d plus 3. So I get b must be, I'll just pick d plus 3. Now I get my n naught as 0 because, as I mentioned earlier, by using this trick where we did the plus a, we've got, our inductive proof works for all of the n from 1 and up. So I pick my n naught to be 1. So I'm done. I've proven what I said I was going to prove, and that ends my upper bound inductive proof. So we've shown an upper bound for our merge sort that this is n log n. For a lot of people, we're done. A lot of times you say, okay, I know that the worst it's going to do is n log n. Maybe this isn't a tight bound, but I'm happy with this. But it is a tight bound, and so we can prove that as well by doing another simple inductive proof. But now we're going to do the lower bound. The lower bound actually turns out to be easier than the upper bound, and that's because we don't have to worry about this canceling out in the base case and the plus a that we added. In this case, we don't need a plus a, so we're just going to leave it out. Just because we had a plus a on the upper bound doesn't mean we need to use it on the lower bound. And why is that? Well, let's just take a look at our base case to make sure. T of 1 is still 3. 3 has to be greater than or equal to this. Well, that's 0. 3 is greater than or equal to 0. That's true for any a. Check, we're done. So the thing that caused us a problem on the upper bound makes it easy on the lower bound. Okay, the inductive hypothesis. This is the same as what we just did in our previous proof, except we've changed our sign to match the sign of the theorem that we've got here, of course. Okay. Again, notice the plus term doesn't show up either because we're not using it. We use the simplified term. Okay, the first step is the same. We'll copy down our term, our definition, our recursive case, because this is the n greater than 1 case. Copy it down. And again, our goal is to apply the inductive hypothesis. So our first step might be n over 2. Is that less than n? Yes, indeed it is. And so that this is a k that we can apply our inductive hypothesis to. So now we need to plug in the n over 2 for our k and make sure we know what that says. That's saying t of n over 2, that's what we have here, is greater than or equal to this term, a n over 2 log of n over 2. Okay, we're going to do that, being careful to remember we had 2 of those terms, so the 2 comes down as well. and then multiplying through, fairly straightforward, the 2's cancel. And actually here I've done the log identity as well. So I've minused off the an. So I did 2 steps at once here. Those are the same steps we just did in the previous proof. So if you need to go back, take a look at those ones. But we can see now the leap of faith is much easier to make because we just have a minus an and a plus dn. And we need, in this case, the positive one to outweigh. So we just need d bigger than a. So we'll pick our d greater than a, or we'll pick a to be equal to b, a equal to d, sorry. And then we're going to have n naught. In this case, again, just looking where did we start out? At 1. It worked for n1, no problem. So we're done. We achieved the lower bound as well. So our recurrence relation, which we're using as an expression of the worst case runtime for our recursive merge sort algorithm, we've shown both indeed a upper bound of n log n and a lower bound of n log n. And in so doing, that establishes a tight bound or a theta bound of n log n as well. All right, this video concludes this series on recursive algorithms. It also concludes this series on discrete math for computer science, and I treat it as a sort of a baby class or an introduction class to design and analysis of algorithms, which I also have a video series on. So if you are completed with this video series now and you're eager to listen to some more or watch some more videos, I suggest either jumping into my data structures video series or my design and analysis of algorithms video series, both of which you are now very able to handle the material in. So thanks a lot for watching, and we'll see you in that next video.